In this module, we will discuss how to apply the root locus to controller design. In the previous module, we introduced a graphical tool called the root locus. And if you recall, the root locus plots all of the possible closed-loop pole locations as a parameter changes. Typically, this parameter is something like a proportional controller gain. We also presented a procedure for drawing the root locus and alluded to the fact that the root locus is helpful for higher order systems. So when we have simple canonical systems, first order, second order, we can just apply algebra to find the necessary gains to meet a specific specification. But for higher order systems, it's much more challenging, and the root locus allows us to see how multiple poles move around as we change a parameter. Specifically in this module, we will discuss how to apply the root locus to controller design. And so we're basically going to present a procedure and some examples. With our procedure, the first thing that we want to do is we want to translate our performance specifications into closed-loop pole locations. Things like settling time requirement, overshoot requirement, etc. Requirements on the transient performance of the system. We then will draw the root locus of the system with a simple proportional controller. Then we will use the root locus to try and identify whether or not there is a design of a proportional controller. Is there a value of the gain k that will meet our given requirements? If yes, then we're done. If not, then we need to try a more complicated controller, and specifically a dynamic controller, where we will add poles and or zeros to change the shape of the root locus so that it will pass through the region where we need the closed loop poles to be located. This may not be entirely clear, but as we go through some examples, hopefully it will become more clear. Let's now try an example to better illustrate the procedure from the previous slide. So in this example, we'd like to find the value of the gain k, where we have a negative feedback system with a simple proportional controller. So we want to find the gain k, if it exists, that provides this system, the closed loop system, a settling time of 4/3 seconds. Okay. So the very first step in our procedure is to translate the specifications into pole locations. So take a second and think about how a requirement on settling time translates to a pole location. Okay, so specifically, settling time is approximately equal to 4 divided by sigma, and we would like the settling time to be 4/3 seconds. So if we then solve this equation for sigma, we can bring the sigma to the right hand side. We can multiply through by the 3 and divide through by the 4, and then we get that sigma is equal to 3. Okay. And so from a first glance, we can right away see that we're not going to have a canonical second order system, because we're going to end up with a 0 in our closed loop system. Despite the fact that this won't be a canonical second order system and this relationship won't hold exactly, the root locus will still be helpful to us as a way to help us know how to tune the gains. The second step in our procedure is to draw the root locus with this simple proportional gain. And so this is something that we did in the previous module. If you recall, you can go back and look at how we did that. So this is the root locus. These lines show all the possible pole locations as we vary the value of k. So when we start with k equals 0, the closed loop poles are located in the same location as the open loop poles, and as we increase k, the closed loop poles move along these branches. Eventually, if we increase k enough, the system goes from being underdamped to overdamped. the closed loop poles go from being complex to being real. That occurs at this break-in point, and then the poles keep going, and the closed loop poles, one of them approaches an open loop pole, and the other one follows along an asymptote that we can think of as a zero at infinity. When we draw the root locus, we also need to include the pole locations corresponding to our specification. So on the previous slide, we found that we wanted sigma to equal 3. And so take a second and think about what pole locations correspond to a sigma equal to 3. Okay, if you recall, sigma is the real part of a pole. So sigma equal to 3 means that our closed loop poles have a real part of -3. This is negative sigma equals -3. So all poles that are on that line will have a sigma equal to 3. Now the question is, can this requirement be met? Is there a value of k? Is there a proportional controller which will give us a sigma equal to 3? So take a second and think about this. So it turns out that the answer is yes. And the answer is yes because there is a portion of the root locus that crosses this dotted line. So there are values of k where we can place the closed loop poles on this dashed line, where this dashed line corresponds to poles with sigma equal to 3. If we wanted to find the specific value of k, one thing that you could do is you could go back to the ultimate requirement of, you can go back to the condition based on which we drew the root locus. And so in this case, this closed loop pole, it has a real part of -3. We don't necessarily know what the imaginary part is, but we know that it has a real part of -3 and it has some imaginary part we could call omega. And so what you could do is you could substitute this value of s into this equation and find a value of k and a value of omega, which will make the two sides of the equation equal. In this class, we won't really do that. Instead, we'll use MATLAB. So this figure was drawn with MATLAB, and from MATLAB we can find the value of k that puts the closed loop poles exactly at this location. So we will use MATLAB to find k. Looking back on the previous slide, we saw that this system will not be canonical. So in fact, it's likely that because of the presence of that 0, that the settling time won't be 4/3 seconds. It could be smaller, it could be larger. That being said, this root locus is still helpful because we can see how change in k moves the closed loop poles. So if we find that our settling time is too large, we can make the settling time smaller by moving the closed loop poles to the left in the complex plane. Moving the poles to the left makes sigma larger, which makes settling time smaller. So recall, settling time is 4 divided by sigma. So if we make sigma larger, we make settling time smaller. So even though we may not have a canonical system, the root locus can still be helpful. If we keep increasing k, then these closed loop poles will keep moving, this one down, this one up, until they hit the break-in, and then one branch will go to the right and one branch will go to the left. And it turns out we could pick another value of k, a value of k larger than the one that placed the poles here at these squares, we can increase the value of k and we can get a pole that also has a real part of -3 for this value of k. So take a second and think about whether or not that value of k would meet our requirements. So in this instance, we'll have one pole with a real part of -3, but we'll have another pole that has a real part that's not -3. However, if you recall that the slower pole dominates, this pole is slower. The pole with the smaller real part is slower. So this pole will dominate. So even though we have two poles where only one of them has the sigma we desire, this pole is faster, and so its contribution will be less, and this pole will dominate. So again, we may not have a settling time of exactly 4/3, but it will likely be close to 4/3 because this is the dominant pole. So this is another example of how using the root locus can be helpful for controller design. So now let's try another example with a different plant and a slightly more complicated specification. So in this case, we want to design a controller. It doesn't necessarily have to be a proportional controller that achieves a peak time of less than 1 second and overshoot less than 4%. So if you recall, the first step in our procedure is to plot the desired region of the closed loop poles that will satisfy our specification. So the first requirement for peak time, we can use the fact that peak time is equal to pi over omega d, and we want the peak time to be less than 1 second. If we solve this for omega d, we can multiply omega d to the right. We get that omega d needs to be greater than pi. In this case, you might be able to see that if we have a simple proportional controller here, then this will be a second order canonical system when we close the loop. And that may not be completely obvious to you, but we can point it out in the next slide. So since we will end up with a canonical second order system, this requirement will be true. We then also have the requirement on overshoot. We know that overshoot is equal to e to the minus zeta times pi divided by the square root of 1 minus zeta squared. And we want that to be less than 4%, so we'll say less than 0.04. If we took this equation here and we solved it for zeta, we would get natural log of 0.04 square that quantity, and then divide it by pi squared plus the natural log of 0.04 again squared. And if we punch that into our calculator, that equals approximately 0.707. If you go through the algebra of solving for zeta, you might have a little bit of a hard time keeping track of the direction of the inequality. So often what you can do is you can just sort of use your common sense, your intuition. If we want overshoot to be smaller than some number, so we want overshoot to be less, that means we need more damping. More damping decreases the overshoot. So that means that we need zeta to be larger than 0.707. Okay. On the next slide, we want to translate this into pole locations. So if you recall, omega d corresponds to the imaginary part of the pole. Zeta, the way that it shows up in the complex S-plane, is based on the fact that zeta is equal to cosine beta, where beta is the angle made with the real axis. So if we wanted to solve for beta, beta is equal to the inverse cosine of zeta, where the inverse cosine of 0.707 is approximately 45 degrees. And again, you may have a little bit of trouble determining the direction of the inequality. If you wanted to, you could always graph this cosine and get a sense of what value of beta would satisfy the inequality that zeta be greater than 0.707. So just real quickly, I'll remind you of what beta is. So beta is that angle. If these are the closed loop pole locations, beta is the angle made with the real axis. So again, you may have some issues trying to recall or figure out what's the direction of the inequality. Should beta be greater than 45 degrees or should it be less than 45 degrees? And so one way to sort of remember this is that if our poles are on the real axis, then we're overdamped and we have no oscillation at all. If our poles are on the imaginary axis, then we're undamped and we oscillate forever without decaying. So basically, as our poles get closer to the real axis, as beta gets smaller, that means that we're adding damping to our system. We're getting closer to overdamped and farther away from undamped. And so using that sort of logic, we need that beta be less than 45 degrees. We need it to get closer to the real axis because we're trying to get less overshoot. So these are our two basic requirements on pole locations. Going to the next slide here, we can then draw those in. So recall that omega d is the imaginary part of the pole, and we need it to be, so omega d equal to pi is that horizontal line, and we need to be above that line. We need omega d to be greater than pi. We also found our beta of 45 degrees, and we needed beta to be less than 45 degrees. So we want to be above this horizontal line and below this angled line. And so the region that satisfies both of those requirements is here. And since this is a 45-degree angle here, the corner occurs at negative pi, a real part of negative pi. And when we're dealing with complex poles, as we are here, the conjugate will always be reflected over the x-axis, over the real axis. So if we place one pole in this location, we're also going to get a mirror image of that pole. So we will also have a desired region down here. At this point, we'll now plot the root locus using a simple proportional controller K. So from the previous slide, we have that our open loop transfer function is equal to K divided by S plus 2 times the quantity S plus 4 for a simple proportional gain. So if you can recall the sort of rules for drawing a root locus, the very first step is to plot the open loop poles and open loop zeros. In this case, we have an open loop pole at -2 and an open loop pole at -4. So we can mark those here. There are no open loop zeros. The next step is we identify where on the real axis the root locus is located. And so it needs to be to the left of an odd number of poles and zeros. So in this region of the real axis, we're to the left of nothing. There are no poles and zeros. And so we're to the left of an even number, and so there's no root locus on this portion. In the region between the two poles, between -2 and -4, we're to the left of one pole. Since 1 is odd, we do have a root locus in this region. And then out here, we're to the left of 2. We're to the left of both poles. Since 2 is even, there's no root locus in this region. Then we determine the asymptotes. In this case, we have 2 more poles than zeros, so we have 2 asymptotes, 2 zeros at infinity. And if you remember the shape of those asymptotes will go up at +90 degrees and down at -90 degrees. It turns out that they're going to go up in this direction. And you may not be able to identify the exact location of the asymptote, but we could use MATLAB to find that value. It turns out that we have a breakout point here between 2 and 4. So branches begin at poles and they go to zeros. So these branches leave the 2 open loop poles, and then they intersect, or they meet, and at the point that they meet, that's where we get our breakout point. So we break out and the root locus will go up, one branch will go up and one branch will go down. And it turns out that this breakout point occurs at -3 and the asymptote stays along the line equal to -3. So now that we've plotted the root locus, we then try to answer the question, can the requirements be met for this controller? Is there a value of k? Is there a proportional controller k for which we can have a peak time of less than 1 second and overshoot of less than 4%? So go ahead and take a look at this drawing and see if you can answer the question. So the answer is no. And the reason the answer is no is because our root locus does not pass through the desired region. This region defines the poles that will provide a peak time and an overshoot that we desire. And this root locus does not pass through this region. It passes just to the right of it. So that means there is no value of k which will put our closed loop poles in this region. And since we have a canonical second order system, you can see that it's canonical because our root locus has 2 branches, so we have 2 closed loop poles, so we're second order, and we can see that there are no zeros. So since this is a canonical second order system, the analysis that we're basing off of this root locus is correct, and so we cannot achieve these requirements for a simple proportional controller. So what we want to do now is to try and add poles and or zeros to our controller to try and bend the root locus into this region. We want to change the shape of the root locus so it passes through the desired region. So what we're going to do is we're going to attempt a PD controller. Momentarily I will try and give you some intuition as to what type of controller to pick in order to bend the root locus into the location that you want. But for now, let's just blindly attempt a PD controller and see if it will work for us. It turns out that a PD controller adds a 0 to the open loop system. And so looking at this, it may not be obvious that this has the form of a PD controller. But if I go ahead and distribute that k, it may be a little bit more clear. You see that we have one term with a differentiator and one term that's a constant. So looking at that, what is our KD for our PD controller and what is our KP? So the KD is the coefficient in front of the differentiator, and the KP is just the constant. So it's our gain k multiplying the 0 location that we've added. So looking back at our original system, we had poles at -2 and -4 from our plant. And so based on that, here we're adding a simple 0, a real 0. And there are basically sort of 3 distinct choices for location of that 0. We can place the 0 to the right of both of the poles, we can place the 0 between the 2 poles, or we could place the 0 to the left of both poles. And so we will try all 3 locations and see if any of them will help us meet our requirements. So first, we'll look at z less than 2. So if we create a 0, s plus 1 or whatever, where z is less than 2, that'll place a 0 in that region. Okay. So then we can follow the same procedure. We have our desired location of the closed loop poles. We place the 0, and then we'll see is there a value of k that will put our closed loop poles in this region. Okay. So we've plotted the open loop poles in zeros. We recall that the root locus is to the left of an odd number of poles in zeros. So this location right here is to the left of 1 element. This region of the real axis is to the left of 2, which is even, so no root locus. And this region is to the left of 3, which is odd, so that is on the root locus. We have 2 more poles than zeros, so we have 1 asymptote, 1 0 at infinity. If you recall, that asymptote will go off at minus 180 degrees. So that will be one branch of our root locus. The other branch starts at an open loop pole and goes to the open loop 0. And so that's basically it. That's the root locus. As we increase k, the closed loop poles start at -2 and -4. The one at -2 moves to the right towards the 0. The one beginning at -4 moves to the left out to infinity, and that's our root locus. So looking at this, is this location of 0 placement something that will meet our requirements? And so of course the answer is no, because our root locus does not pass through the desired region. So these closed loop poles won't provide us the peak time and the overshoot that we desire. The addition of this 0 makes our system non-canonical, so it may be a little hard to tell, but we have a pretty good guess that that 0 location won't help us. So let's go ahead and try a different 0 location. In particular, we'll try one between the 2 poles. So we'll place a 0. So we'll place a 0 between 2 and 4. Again, drawing the root locus, we have the root locus on the real axis to the left of an odd number. So that's to the left of 1. That's to the left of 3. We again have an asymptote going off to -180 degrees. We we again have a branch that starts at the open loop pole at -2 and goes to the open loop 0. It's just now that branch goes to the left instead of to the right because we placed that 0 to the left instead of to the right. And then we're done. And so again, this is the root locus. It does not put closed loop poles in the desired region. And so this location of our 0 doesn't meet our requirements either. So the last sort of region, or last chance, is to try 0 that's larger than 4. That's to the left at the open loop pole at -4. So again, we draw the root locus. We're to the left of 1, which is odd, and to the left of 3, which is odd. We still have 2 poles and 1 0, so we have 1 asymptote going off at -180 degrees. In this case, we will now have a breakout point because this branch starts at -4, this branch starts at -2. As we increase k, the closed loop poles move away from the open loop poles. Eventually they'll meet, and at the point at which they meet, we'll have a breakout point. Okay. And then those branches need to approach a 0. And so here we have a 0, and out here it's like we have a 0 at infinity. So between two zeros we often have break-in points. We generally have break-in points. And between open loop poles we generally have breakout points. So we break out, and these two branches, one is going to be trying to get to that 0, the other one's going to be trying to get to the 0 at infinity. And so they break in, and one goes to that 0 and the other goes to the asymptote. And so this is the shape of the root locus that we arrive at. We draw in our region that we're trying to achieve, and since we don't know the exact shape of this circle, we don't know for sure if we can make the root locus pass through that desired region. It seems possible, because basically as we change the location of this 0, we'll change how big this circle is. So it seems possible that we could find a 0 location that makes the circle big enough to pass through that region. But we don't know for sure. It's a maybe. And so what we'll do in this class is we will use MATLAB to figure out for sure. And I'll show you in a second how to do that. Okay. So can the given requirements be met by this controller? It seems maybe. We'll go ahead and use MATLAB and sort of do guess and check. Maybe we'll try a 0 at -5. Maybe we'll try a 0 at -10. And we'll play around with that 0 location and see if we can get the root locus to pass through the desired region. Again, since our system is not canonical because we added this 0, we can't be for certain, but since we're using MATLAB, we can go ahead and graph the closed loop step response for a particular value of z and a particular value of k and check if our requirements are indeed met. Before we move on, it was interesting to see that the PD controller added a 0. What if we had attempted a PI controller? It turns out that a PI controller a 0 and a pole at the origin. Okay. And so that may not be absolutely obvious. So let's go ahead and recall. So a PI controller has a proportional gain, and then it also has a coefficient on an integrator. If we get a common denominator, we need to multiply and divide this term by s. And then we can rearrange the PI controller into that form. And you can see that we have a 0. There's a value of s that will make the numerator equal to 0. And we have a pole equal to 0 at the origin. So this has the basic form of some gain multiplying a quantity s plus z divided by a pole at the origin, divided by s. In the previous examples, I basically just gave you the controller to try, or we just picked it blindly. At this point, we'll now try and provide a few sort of guidelines to help us determine whether or not we should be attempting to add a 0 or a pole to our controller. Should we be attempting a PD controller or a PI controller, or what? In general, adding a 0 tends to pull the root locus towards the left, which tends to make the system more stable and settle faster. By moving the poles to the left, they have a larger sigma, so the settling time tends to be smaller. Adding a pole tends to have the opposite effect. It tends to pull the root locus towards the right, closer to the right half plane, so that the system is generally less stable, sigma is smaller, so the settling time tends to be larger. It settles more slowly. An exception to this is when you put a pole near a 0 or a 0 near a pole, and the effect of that is basically a pole-zero cancellation. So if you place a pole near a 0 or a 0 near a pole, it tends to reduce the effect of those poles and zeros. At this point, I'll now go ahead and open up MATLAB and try and show you how to use MATLAB to draw the root locus and to design controllers. Some of this may be a little fast or a little hard to follow. A reference that you can go back to is here's a web page that discusses the use of MATLAB for controller design using the root locus. You can also use the various help through the MATLAB software or the MathWorks website. So first, we'll create a system, a transfer function corresponding to the plant of the very first example that we looked at in today's module. We begin by defining the Laplace variable s. We can then create a transfer function. From the first example, that system had a 0 at -2, and it had a denominator of s squared plus 2 times s plus 3. And so we can plot the root locus of this open loop transfer function using the command RLOCUS. And so what this does is it treats g as the open loop transfer function, and it makes the presumption that there's a parameter k that's multiplying this open loop transfer function. And then it draws the root locus varying k from 0 to infinity. And so this is the picture that we recall. And in that example, what we were trying to achieve was pole locations with a sigma equal to 3. And so one way to do that, so you can see here -3, you can imagine a pretend line here, an invisible line here. If we come up here and click on this data cursor, what it does is, and then we click on the root locus and we move this around, it shows different points on the root locus, and it shows the gain, the value of k that places the closed loop pole there, tells you what the exact pole location is, and then it also tells you these qualities: damping, overshoot, and frequency. But these properties are only if that pole belonged to a canonical second order system. So in this case we have a 0, so the overshoot would not actually equal 2.71. But anyways, we're trying to achieve a pole with a sigma equal to 3 that is a real part of -3. So if we keep moving this cursor around, we can see that we have a pole that's close between these two locations here. There's a pole of -2.83 and there's a pole of -3.06. And in essence, those points that it's jumping between are the points that MATLAB calculated in generating the root locus. So recall that MATLAB generates the root locus in a brute force sort of manner. It starts at k equals 0 and it steps up values of k, calculating new closed loop pole locations, and then it draws a continuous line to connect the dots. If we want to try and interpolate between those 2 points a little bit, what we can do is the following. So we can right click, and in the selection style, instead of snapping to the nearest data vertex, we can go based on mouse position, and that will allow us to get in between values. So there I'm able to place the pole with a real part of -3, and you can see that the corresponding gain is 4. Here we had a plant with 2 poles, a pole at -2 and a pole at -4. So that's our transfer function. We can again use the RLOCUS command. This is the same root locus we generated by hand. Looking at this, you'll have to sort of imagine the region that we were looking for. Recall that it was a sort of a triangle that was above. It was above a horizontal line at pi and below an angled line at 45 degrees from the origin. And so right now this is too small to see the region, but we know that it didn't work. And we also knew that by placing a 0 out here to the left of -4, we thought we might have the opportunity to bend the root locus into the desired region. So now we can create a new transfer function with an additional 0 and see if we can indeed get the root locus bent into the desired region. And so we can create an entirely new one, or we can just take the one that we had and add a 0 to it. We want to be to the left of -4, so we'll just go ahead and try a 0 at -5. And we get the sort of shape that we were anticipating with this circle. So looking at this, we want to get above a horizontal line of pi. We're not there yet. We're below 2. So I'll go ahead and try a 0 that's farther to the left. So instead of s plus 5, let's try s plus 10. Look at the root locus, and that made the circle larger. And so now it's looking possible here. So here approximately is a horizontal line at pi, or around 3, and so we've definitely gotten our circle above it, and you can sort of imagine an angled line. So in essence, we need our imaginary part to be greater than pi, and we need our real part to be greater than our imaginary part in order to get it under the -45 degrees. And again, we can use this cursor, click on the circle. Here we've got an imaginary part greater than pi, and we've got a real part that's larger. So this indeed satisfies our requirements. And something like this might put us more safely in our region, or even something over here might put us more safely in our region. So this gives us our gain and our pole location. So it does appear indeed that we can use a PD controller in order to achieve our desired pole locations. another command that can be helpful is the Arlo Client command. So before we call this command, let's go ahead and go back to the original transfer function we had from the first example and draw the root locus for that. For that system, if you recall, it looks like that. And then we'll call the Arlo Client command. And on the left hand side, we give two outputs, K and P. And on the right hand side, we have the command Arlo Client, where we give as an argument the open loop transfer function that we want to draw the root locus for. And so if we hit return, what it'll do is it'll take the root locus and it'll add these crosshairs. And what these crosshairs allow you to do, if you pick a point on the root locus, what will be returned is K, which is the value of the gain that places the pole at the location you clicked on, and then P, which is the location of all of the poles corresponding to that K. So for this example, we have a second order system. So if we clicked on one point, it would give us the value of K that places the closed loop pole at that location, but it would also return other poles. Since this is second order, it would return both poles that are placed by that value of K. So for example, we had discussed how if we had placed a pole exactly at -3, we would get one real pole at -3, but we would also get another pole out here to the left that was faster. So let's go ahead and click on this point -3. And we can see that the value of the gain that places us there is approximately 6. And it looks like we get a closed loop pole at -3 and another closed loop pole at -5. So this can be a helpful command. Another helpful command that is actually quite powerful is called the RL tool command. And you can also call it via the CISO tool command. But we won't get into that during this module. That's something we'll discuss later on. Returning to the PowerPoint presentation, that brings us to the conclusion of Module 18. In this module, we discuss how to use the root locus in order to design controllers. And in particular, we introduced a procedure where we first translate performance specifications into closed loop pole locations. We then draw the root locus for a simple gain K for a simple proportional controller, and we see if that gain change can meet our requirements. In other words, we see, is there a value of K that puts the root locus in the desired region, that puts the closed loop poles in the desired region? If yes, then we're done. If not, then we try a more complicated controller. We try to add poles and or zeros in order to reshape the root locus to bend it into the desired region. We learned some basic guidelines that zeros tend to pull the root locus to the left, poles tend to pull the root locus to the right, and placing a pole near a zero or a zero near a pole tends to cancel out the effect of those poles and zeros.